Let's take a look at an open box optimization problem. This is a fairly standard problem in a basic calculus course, the open box problem, and there are a few different angles that they can take on it. This one is giving us different prices for the base of the box and the sides of the box and asking us to optimize the cost. So we want the cheapest container we can possibly make given the information that they're giving to us. So I've drawn the open box, the basic skeleton of the open box. It's going to look the same pretty much every time. This one is an open box with a rectangular base. Sometimes they give it to you with square bases, but this one's a rectangle. And so I've drawn the base, and then I've drawn the four sides, which you would fold up. And if you fold those sides up, you would end up with an open box. So let's go ahead and label this based on the information that they're giving us in the problem. They're telling us that the length of the base is twice the width. So if I make the width of my base be x, then the length is going to be 2x. It's twice as long. So I'll go ahead and label all of those. So those dotted lines along my base, those are x and 2x. I need something for the height too. The height is just when I fold up these flaps, I've got a height here that I'm going to call y, and every one of these is y, because when we fold them up we want them to meet at the top so that we have an even top to our open box. Okay, what else are they telling us? They're telling us that the material for the base costs $15, so it's going to cost $15 per square meter here, and then for each of the sides we've got $9 per square meter. All right, and so we're on our way to being able to come up with a cost function, but first I want to take a look at this information that they're giving us about the volume. They've told us that the volume of the container is 10 cubic meters, and we remember from geometry and from elementary school actually that the volume is going to be length times width times height. And so we've got all of those things here. So our volume is going to be length times width. So that's going to be x times 2x times y. Well, that's just 2x squared times y. And they've also told us that that equals 10 cubic meters. So that equals 10. So what I'm going to do right now is I'm going to solve that for y. I know that when I come up with my cost function, I need it to be all in terms of one variable so that I can take a derivative. So I'm going to want to make sure that I have something that I can plug in for y's so that I can get rid of all of the y's in my cost formula. So y is going to equal 10 over 2x squared, and so that's just 5x to the negative 2. And I'm writing it with that exponent because it's going to be easier to take the derivative with the exponent in the numerator. Okay, so we've got that. So let's come up with a function for the cost of this thing. So I've got cost, and I'm going to try to do this in terms of x. I'm going to have some y's the first time I write it out, but once I have it written out, I can go in and everywhere I have a y, I can plug in this 5x to the negative 2. All right, so how much is it going to cost me to make this thing? It's going to cost me $15 per square meter for the base. So I have $15 times the area of the base. Well, the area of the base is 2x times x, so that's 2x squared. Now I've got four sides. Two of them are identical and the other two are identical, but I do have to address these differently because they're different sizes. So let's look at these two long ones first. I have two of them. They are $9 per meter apiece, and the size of them, those are 2x by y, so 2xy. Okay, and then I have my two shorter flaps. I've got two of those. They are also 9 apiece, and they are x by y. All right, and so that covers the cost of everything. I have $15 for the base. I've got $9 for two of the longer flaps, and I've got $9 for two of the shorter flaps. Let's clean this up a little bit. So we have, let's see, 15 times 2x squared is going to give me 30x squared. And then here, my y, I'm going to be plugging in 5x to the negative 2 for that. So I've got, let's see, 9 times 2 times 2, that's going to give me 36x times 5x to the negative 2. So I've just multiplied everything together and plugged in the y. Same idea here. Now I'm going to have 18x times 5x to the negative 2. Okay, so we can clean this up just a little bit more. We want this as neat and nice as we can get it before we start taking a derivative. Okay, so we've got 30x squared plus, well, 36 times 5, that's going to give us 180. X times x to the negative 2 is going to give us x to the negative 1, plus 18 times 5, that's 90. X times x to the negative 2 is x to the negative 1. And then in one more step, we've got 30x squared, and if we combine these two terms, we get 270x to the negative 1. Okay, that looks like a cost function. It's all in terms of one variable. So I'm going to take the derivative, because that's what we do with optimization problems. So the derivative, c prime of x, is going to be 60x minus 270x to the negative 2. Once I have the derivative, the next step is to set it equal to 0 and solve. So we'll do that. 60x minus 270x to the negative 2 equals 0. There are all sorts of ways you can handle this algebraically. I like to get rid of the negative exponents, so what I'm going to do is just multiply both sides of this by x squared. So that's going to give me 60x to the third minus 270 equals 0. And you can do the algebra however you want to do it. So this is going to give me 60x to the third equals 270. So x to the third is going to be 27 over 6. And if you do that in your calculator, if you take the cubed root of 27 over 6, you're going to come up with a fairly long number, 1.65096, I think is where I left that at. All right, so that tells us how long x is, but the question they're asking us is how much it's going to cost for the cheapest container. So I need to take that x and do something with it. I need to find the cost. The way I'm going to find the cost is by plugging this x value into the cost function. So to answer my question, I need c of 1.65096. So that'll be 30 times 1.65096 squared plus 270 times 1.65096 to the negative 1. And if I plug that into my calculator, I'm going to get something that is roughly, well, it will round to 245.31. And so that would be the cost of the cheapest container. So let's walk through this again, make sure that you understand everything that we did. The first thing we did is we labeled our open box. We were told that the length was twice the width, so I have x and 2x for my width and my length. They told us the cost of the base was $15. They told us that the cost of the sides were $9 a piece, and that was per square meter. Using the formula for volume, I was able to take y and write it in terms of x. So I used the formula for volume, set it equal to the 10 cubic meters that they gave us in the problem, which gave me y equals 5x to the negative 2. And the reason I did that is because when I write out my cost function, I'm going to have y's that need to be plugged in later. All right, so let's look at the cost function again really quickly. It was $15 for the area of the base. So that's 15 times 2x times x, or 15 times 2x squared. I have two long flaps, and my long flaps are 2x wide by y long, so those are going to be two flaps, $9 a piece, times 2xy, which is the area of those flaps. The shorter flaps are only x times y for their area, so I've got two of those at $9 a piece, times x times y. I started multiplying things together, plugging in my y's, and ultimately I came up with a cost function of 30x squared plus 270x to the negative 1. When I had the cost function, I was able to take the derivative. I then set the derivative equal to 0, solved for x, and came up with an x value. The question didn't ask me about the x value, the question asked me for the cost, so I used that x value to plug it into my cost function, giving me $245.31.